Okay, let's go back down to Earth and let's continue to look at some examples of conservation of angular momentum. You know, when we studied linear momentum, one of the areas of great importance for the application of linear momentum was collision. In a collision, the force between two objects in collision can be brief but very violent. It is often not possible to trace the exact sequence of the collision, what happens, how the force starts and ends, because it's a very rapid and violent process. However, if the net force, the net external force on the system which consists of these two objects in collision is zero, then something does not change as a result of the collision, and that is linear momentum. Okay, we have here angular momentum, right? And can we apply conservation of angular momentum to a collision process involving rotation? Well, the answer is definitely yes, if you've observed the right condition. What is the condition for angular momentum to be conserved? No net torque. Okay? You know, it is possible to have a net force and yet no net torque as long as that force does not produce any torque. How does a non-zero force produce zero torque again? Because it is possible for the lever arm to be zero, right? Okay, let's take a look at an example. The application of conservation of angular momentum in a collision process. What we have here is a uniform rod of length L. Okay, from here to there, the length is L. The mass is m2. The center of mass is right in the middle. It can rotate in a vertical plane without any friction about 0.0. That's a fixed point. Okay, imagine this. A small sticky object, pullywad, mass m1, moving with a speed v1 horizontally, comes in and aiming at the lower end, point A of the rod end, and hits that point and sticks to it. Okay, sticks to it. So as a result, the rod, now with the point mass at the end, will start to rotate upward, right, in a vertical plane. It can reach an angle theta before it comes to a momentary stop. Okay, before it comes back. Suppose you know all the necessary geometrical data and the mass, m1, m2, L, v1. Can you find that theta for me? How high will the rod be able to move upwards before it stops momentarily? Now, let's analyze this problem. Okay, I can think of this problem in two stages. One is the collision process between the small point mass and this rod. During that collision process, is there any conserved quantity? Well, we have learned three possible conservation laws: conservation of mechanical energy, conservation of linear momentum, and conservation of angular momentum. Okay, let's look at them one by one. First of all, do you have conservation of mechanical energy? Well, that depends on is the collision elastic or not. Okay. This mass sticks to the rod. It sticks to the rod. What is the nature of the force that makes it stick? Well, that's friction. Okay, so you have friction force involved, and that in fact is what's called a complete inelastic collision. Why? Because the two pieces get stuck together after the collision as a result. We know in a complete inelastic collision you don't have conservation of mechanical energy. In fact, part of the initial kinetic energy of this point mass is turned into heat. Okay, you don't have conservation of mechanical energy. So, what's next? How about conservation of linear momentum? Well, what is our system? Our system involves two objects, m1 and m2. Okay, what is the criterion for the linear momentum of the system to be conserved? Well, the criterion is that there cannot be any external force, right? Okay, the collision force between m1 and m2, of course, that's internal, because it's from part of the object, part of the system to another part of the system. The question is there any other external force? Is there any other force from outside the system that exerts on the system during the impact? Well, we have gravity, gravitational force. We don't worry about it because that's a vertical force, and you know the collision happens. I'm only looking at what happens horizontally. Plus, gravitational force is not very significant for the very brief moment of collision. Okay, and the other type is the contact force. You know, the system is the rod plus this mass, right? It is only in contact with the outside world at point O. is there a force of impact at point O delivered from the ceiling through the hinge at point O to the rod? If there is, that is an external force, and that will ruin conservation of linear momentum. All right? Okay, I don't know if that's the case. I speculate that there must be a force of impact here, but suppose I didn't know that. Suppose I assumed that there were no force here, no impact force here. So I could then use conservation of linear momentum, right? What would happen if I did so? Well, then I would be able to write down the speed, the common speed of the rod and this point mass as a result of the collision. All right? Well, let's see how we can do that. Okay, let's see how we can do that. Using conservation of linear momentum, assuming that it's conserved, I have initial momentum, P initial, right before the collision. It's borne only by this guy, right? M1, M1. There's no question about that. P final, right after the collision. Okay, the rod hasn't started moving up yet. It's just right after the collision ends. What's that equal to? Okay, let's say the end of the rod, point A, is now moving at speed v. Okay, so I get m1 v. What is that? That is the linear momentum of the point mass after the collision, because after the collision it's stuck at point A, which is moving at speed v. Now, if point A is moving at speed v, how fast is the center of mass moving? Now remember, the center of mass, just like point A, after the collision, it is rotating about point O, right? And since the center of mass is halfway between point A and point A, as point A moves with speed v, the center of mass must be moving at half that speed, right? Because they have the same omega, but they don't have the same linear speed, because this is moving with half a radius compared with that. So, as far as the rod is concerned, I use the center of mass linear momentum. That will be m2 times center of mass speed, that is v over 2. And let me equate P initial equal and P final. Okay, let's see what we get. So P initial equals P final. Don't know if it's right, but if it were right, then I would get M1 V1 equals to M1V plus M2 V over 2. And I would, what did that tell me? I would be getting that the final speed V to be equal to M1 V1 divided by M1 plus half of M2. Okay, is this right? So what I did was I used conservation of linear momentum for the collision. Now, let's see. What is the last conservation law, the one that we just learned? That's conservation of angular momentum, right? What is the condition for angular momentum to be conserved? Well, the condition is that there be no external torque for the system. Okay, you don't worry about the force between these two because that's internal. You don't worry about gravity because, first of all, gravity is insignificant during the collision. Secondly, even better, gravity acts on this line and that passes through point O. If I use point O, which is of course a fixed point, I can use point O as the observation point because it's fixed. It has no lever arm, right? Okay, thirdly, the only trouble we had was we were not sure whether or not there was an impact force here. Okay, but if there were the impact force, that would have ruined conservation of linear momentum. This whole thing would be wrong, right? But you can still use conservation of angular momentum. Why? Because any impact force would have to go through that point O at the hinge. And therefore, relative to point O, the lever arm of that force would simply be 0, right? Suppose you had a force like this. It goes right through that point. Okay, so no matter how strong that force is, it does not produce any torque about point O. And therefore, I know with no dispute that I can use conservation of angular momentum about point O. So let us write down conservation of angular momentum and see if the result agrees with conservation of linear momentum. If that agrees, that means linear momentum and angular momentum are both conserved. And if it does not agree with that, then we must say that angular momentum is conserved but linear momentum is not, because it does not agree with conservation of angular momentum. So let's see now. Before the collision, what is the angular momentum of the system measured at point O? Okay, I'm using point O as a reference. So angular momentum for about point O. Before the collision, this is the only mass, M1, that has angular momentum. It's a point mass, so remember the formula, R cross P, Okay, it is right here before the collision, right? So R is like that, P is like that. So R cross P, it's a vector sticking out of the paper, and the magnitude is this R times this P times the angle between them, which is 90 degrees. So PL initial is simply equal to M1 V1, that's P initial for the point mass, times the distance between here and there, that's L. That's L. Let me use cursive L to differentiate from angular momentum. Okay, that is the angular momentum of the rod plus the point mass system before the collision. After the collision, they got stuck together. Okay, they got stuck together. They now have the same omega value. They have the same omega value. So, what is L final? There are two things you can do at this point. You can treat the rod plus the point mass as a single object, and find its I times omega. Or you can separate them, considering the rod and the point mass as two objects. You find their angular momenta separately and you add them up. Okay, let's say we're going to treat them as a single object. So what is the rotational inertia about that point? Let's say that's I final, and then you can find omega afterwards. Okay, that is the common omega for the rod plus the point mass right after the collision. I'm going to find that out. What is it equal to? What is I final? Well, you got two things: the rod plus the object hanging at its end. Okay, the rod has an angular moment, has a rotational inertia about 0.0. It's 1/3 m1 m2 L squared, right? Plus, there is a point mass here. That point mass is a distance L away from 0.0, so it contributes this much, m1 L squared. That is omega. That is I final times omega. From that, you can find omega by equating L initial and L final. Conservation of angular momentum, we know this is definitely true. Let us find omega. Once we find omega, we can find the speed v here, right? Because v is the linear speed at point A. The angular speed is omega, and that is the distance L away from the center of rotation. So v would be equal to omega times L, wouldn't it? Okay, omega times L. I know what omega is from right here, so let's equate these two, L initial and L final, and solve for omega and then multiply by L. Let me find v. Some very simple algebra, equating these two, and using v equals omega L, this is what v that you get. M1 V1 divided by M1 plus 1/3 M2. Now you compare with this. That was from conservation of linear momentum. This is from conservation of angular momentum. Do they agree with each other? Not quite. Okay, there is this 1/3 here, and here is only 1/2. See that? Only 1/2. So these two expressions do not agree with each other, but we know for sure that we have conservation of angular momentum. This is certainly correct. This is certainly correct. That means this must be wrong. You don't have that. Okay, so this is wrong. What does that tell us? It tells the linear momentum is not conserved during the impact. And why is that? Because there must be an impact force here. There must be an impact force, and that force is external, and therefore you don't have conservation of linear momentum. But you do have conservation of angular momentum, which is why we're studying conservation of angular momentum, because it provides us with a new way of treating a collision process in which linear momentum is not conserved, but this new quantity, angular momentum, is still conserved. Now, let's continue with this problem. We already discovered that in the collision process, you must use conservation of angular momentum, and that's how you find the angular speed, omega, right after the collision. Okay, what happens next? Well, the whole thing is going to start with this angular speed, and it's going to swing up, right? It's going to swing. As it swings up, okay, it can rotate frictionlessly about this hinge. So as it swings up, it's certainly going to lose kinetic energy because it slows down. Okay, at this point, it lost all of its kinetic energy. It's not moving at all. What is conserved from here to there? Well, you don't have conservation of linear momentum because there is certainly a force here, and there is gravitational force, of course. That's also external. You don't have conservation of angular momentum because the gravitational force from here and from here does provide a torque relative to 0.0 once it leaves the vertical plane, right? So what do we have left? What about energy? What about mechanical energy? What is the condition? All forces doing work must be conservative. That's the condition, right? Okay. How many forces are involved? Well, we have the gravitational force. That's a conservative force. But we also have a force here. Do we worry about it? No, we don't, because that force is acting on that corner of the object which does not move. Okay, so no work is done by that force. We don't worry about it. We have conservation of mechanical energy. This is why I said you need to divide this problem into two stages. Stage 1, collision. Stage 2, upward swing. The reason why you want to divide in two stages is because there is not a single conservation law that applies to both of these two processes, two stages. You must break it down mentally into collision stage and swinging up stage so that you can apply conservation of angular momentum to the first stage and conservation of mechanical energy to the second stage. Okay, for the entire process going from here to there, nothing is conserved. But for the first stage, conservation of angular momentum. For the second stage, conservation of energy. Okay, so now we're ready to solve for this angle theta. We know the angular speed omega right after the collision, right? So what is the kinetic energy of the system right after the collision? Well, that I can find out. It is equal to E initial. Now this is the initial state, this is the final state. Okay, E initial, what is that equal to? It's only kinetic in nature. Assuming that initial potential, gravitational potential energy is 0, I can always do that. What is that equal to? Well, one thing is I can think of the rod plus the object at the end as one single object, and everything's rotating about 0.0, so we only have rotational kinetic energy 1/2 I omega initial squared. Omega initial is that omega that we just calculated over there, okay? So we know what it is. What's I? I is, again, the sum of 1/3 ml squared m2l squared plus another m1 l squared, because there's a point mass here. Okay, so let's plug it in. That's 1/2 of I omega 1 squared, 1/3 m2 l squared plus m1 l squared. Omega, I already calculated from here. Okay. In fact, I calculated V, not omega. Omega is just V over L. So as far as omega is concerned, here is omega. M1, copying this. Okay, I'm just copying this. I'm just taking this V here divided by L, and then I get omega. So it's M1, V1 over L. Don't forget over L, because I'm calculating omega, not V, divided by M1 plus 1/3 of M2. There we go. That is omega right after collision. You square it. Okay, you square it. That becomes the initial kinetic energy of the rod plus the hanging of the object at the end right before it starts to swing up, but right after the collision. What should it be equal to? Well, you have no gravitational potential energy to begin with, but as you swing up, you're going to gain gravitational potential energy by spinning your kinetic energy. When you reach an angle theta, you lost all of your kinetic energy. I'm sorry, you lost all of your kinetic energy. All you have is gravitational potential energy. So how much gravitational potential energy did you gain? Well, let's see. For the rod, you look at the center of mass. Okay, it initially was here, initial position, and finally it was there. It went through an arc like that. Okay. This arc is part of a circle of radius L over 2, right? So it went up by this much. By this much. How much is that? Well, that is this distance minus that distance, right? From here to there, that is L over 2. And from here to there, that would be L over 2 times cosine theta. So this distance, let's call it H2. What's H2 equal to? H2 equals to L over 2, which is from here to there, minus distance from here to there, that is L over 2 cosine theta. That's how the center of mass of the rod goes up. Okay, meanwhile, what happened to the point mass? It went up from here to there, from here to there. Let's call it H1. For this guy, it went up by H1. H1, how do you compare with H2? Well, the only difference is it goes through an arc with twice the radius, right? So H2 is 2H, H1 is 2H2. So H1 is simply L minus L cosine theta. All right, so the point mass went up by H1, the rod went up by H2. How much is the increase in potential energy for the point mass? That will be M1G times H1, right? How much does the potential energy of the rod increase? That will be M2G times H2. Okay, so there we go. Let us write down the final energy. The final energy is all potential because the initial potential energy is 0 and the final kinetic energy is also 0. E final is U final. That equals M1G H1 plus M2G H2. Okay, let me write down H1 and H2. H1 and H2, they're right here. So that will be equal to M1G times H1. Okay, so take that L out, 1 minus cosine theta, and then plus for M2G times H2, we take half of L out, 1 minus cosine theta again. Okay, E initial equals E final. Okay, so you equate these two. So this expression equals that expression. You know everything here, okay? You know, M1, M2, L, V1, and everything. And on this other side, the only thing you do not know is cosine theta. So you can then equate these two. You can solve for cosine theta. You can figure out how high it can swing before it stops. So the what's left, the algebra, is trivial, but we got the method how to do this problem. So to recap, again, what we did was we equated. The key idea was to break this process down into 2 steps, collision and swinging, and apply the correct conservation law, which is the conservation of angular momentum, to the first step, collision. The reason why we could do that was because there was no torque about 0.0 during the impact. Okay, and then second step, when it swings up from here to there, right after the collision to when it stops, conservation of mechanical energy. So you trade your initial rotational kinetic energy for the final increase in potential energy. That's how you found the angle of swinging. And the idea of breaking, you know, a process down into 2 steps or more and applying the correct physics, or, you know, say the correct conservation law to each step is very important in solving problems like that.